Welcome to a lesson with Dr. Pal. Let's take a look at the sequence. A sub n plus 1 is equal to the square root of 8an minus 15 when a sub 0 is equal to 4. So that's where we're starting. And this is a recursive definition for the sequence. Let's show algebraically how we can conclude that if we start at 4, that we're going to be bounded above by something. In particular, let's use our intuition from the picture that we've already seen for the sequence, that we're going to be bounded above by 5. So let's use the fact of where we start, because if you notice in that picture, if we were to start after 5, we know we're going to be bigger than 5, right? So that won't work at all. So really, where we're starting should be used in the in our argument. In particular, some knowledge about this. In particular, why don't we just assume that it's less than 5, that we're starting less than 5? So let's just assume that wherever we are in our sequence is less than 5. Can we use this fact then to show that the next place in our sequence will also be less than 5? Now, if we can show this, we've shown it all. We've shown that all the elements in the sequence will be less than 5, because think about it. If this place is less than 5 implies that place, then since this place is less than 5, then the next place will be less than 5. Since that place is less than 5, then the next place, and so forth on forever. So if we can just show at any position we're less than 5, then the next position will be less than 5. We're good, no matter what that position is. Okay, so let's start here and see if we can somehow use that to show that. How do we move a sub n to a sub n plus 1? Well, we're given a formula for how we move from one point in the sequence to the next. Let's see if we can do this. Okay, so we're trying to show that everything is bounded above by 5. So let's just start with our assumption. A sub n is less than 5, and try to turn this into looking like a sub n plus 1. Well, first let's multiply both sides by 8. So 8an is less than 40. Then let's subtract 15 from both sides. Let's see, 40 minus 15 is just 25. And then let's take a square root. Now, can we take a square root of both sides and the inequality be preserved? The answer is yes, because a square root function is an increasing function. And that means that order is preserved. Imagine like from a to b, and output of square root of a, output of square root of b. Notice that the order is preserved because there's a positive rise for a positive run. That's because it's increasing. So for any increasing function at all, we can always take a square root of both sides, and the inequality is preserved. Well, this has shown it, because this right here is a sub n plus 1, and that's less than 5. So we're done. We've just shown that if we start at some point where this is true, and of course it's true right there, then forever on, as we go with this definition for how to get to the next place in the sequence, we will be less than 5. Hence, we have just shown that the condition necessary for the monotone convergence theorem to apply to this sequence with this starting point holds, the one about being bounded above by a number. Now we've shown this algebraically. So that's that one condition. Now, to show that it's an increasing sequence, it suffices, just look at that picture, how if we graph a sub n versus a sub n plus 1, and notice how we're above the line right here. We're above the line, and that means that we're increasing. The sequence is increasing, especially if we start at 4. And so we're just going to be using this technique going like this, and we're increasing this way. So we know we're increasing since this line is above, and we know it's bounded above by 5. Thanks for watching.